Hi everyone, welcome back. Today we're doing count items matching a rule. We're given an array items where every single item is a list of size tree, type, color, and name. And this describes the type, color, and name of the current ith item. You are also given a rule represented by two strings, rule key and rule value. And the ith item is said to match the rule if one of the following is true. Rule key equals to type and rule value is equals to type. So we have to return the number of items that match the given rule. So let's see, if you have phone, blue, and pixel, computer, silver, Lenovo, first value is the type. So in this case, the first type is a phone. The second type is blue. The third type is the name. So computer, of color silver, and of name Lenovo. The third item is type phone, color gold, and name is iPhone. And the rule key in this case is color, and the rule value is silver. So in this case, what this means is that if the rule key is color, it means that you are trying to filter by color, and you're trying to filter for items that are silver. So in this case, we will look at the second column or the first item in each row. And in this case, the item that matches it is the computer that is silver. So yes, this is the answer. Let's go through the second example. So you have a phone that is blue, name pixel, an item of type computer that is silver, and its name is phone. And in the third row, the type is a phone, the color is gold, and the name is iPhone. In this case, we're trying to filter by type, and we're trying to filter of all the items whose types are phones. So in other words, it's the first column, first, second, and third. So in this case, there's two items that matches that, so we'll return two items. So in this case, the output is 2. So okay, we are returning the number of items that match that rule. So in this case, the item's length is up to 10 to the power of 4, pretty lenient. And the type, color, and name length range from 1 character to 10 characters. And rule key is equal to either type, color, or name. Okay, very interesting. And all strings consist of lowercase letters. Okay, looks fine. So in this case, it seems that we have to do some if-else statement to figure out which rule are we trying to filter the items by. And we will use the rule value to filter on the column that is determined by rule key. So yeah, sounds pretty okay. So we will need a linear scan across items, and before that we'll have to figure out which column should we filter the items by. So for example, if your items is this list of size 3, then we have to figure out which column should we use to filter the items by. So to figure out which column we should use, we'll be using rules key. And in this case, we are pretty lucky because rule key only has 3 possible permutations. So if rule key is type, then we will use column 0. Otherwise, if rule key is of type color, then we will use column 1. Instead of column, let's just use index. And if the rule key is name, then we'll use index 2. And in this case, the rule value would just be what we'll be using to match the index for each item by. So yeah, looks pretty good. So the first step for this algorithm would be to do some checks on rule key, and we can assign each rule key to a corresponding index. And based on this index, we can just check if the item at that index is equals to row value. So looks pretty simple. Let's try coming up with a simple algorithm. Let's have a row key to index, and we just define a dictionary of type string to integer, and we can initialize this to be one of the 3 permutations. So if we are given type, we will give it an index of 0. So we will use this index to get the corresponding item in items. The color in this case will be, it will be the second index, or index 1. And for name, we will give index 2, and we use this second index, this 2 index, to get the corresponding item from this list inside each of these item. And the idea is we will get the row index by passing the row key as the key into this row key to index. And we can proceed to do a simple for iteration for item in items. We can just say row value, current row value, to be equals to item at row index. And we will just check if we will just have a additional variable to keep track of matches. So matches equals to 0. And if the current row value is equals to row value, then we will increment matches by 1, and we just return matches. So, but in essence, the idea is we are mapping the row key to the corresponding index of each item. And we will use this index to get the corresponding value that we want to compare with row value. And we will just keep track of an additional integer to keep track of the current matches that we have that corresponds to the row key and the row value. So looks pretty good. And in this case, this looks like a pretty efficient way to go about it. Let's start implementing that. So let's go. So first thing, we will define the row key to index. And we will set this to type, color, and name. And in this case, we only have 3 possible permutations for row key, so this looks great. Now let's define the row index, row key to index, and we will pass in the row key to get the corresponding index that we will use to get each value in each item. Now we can start iterating for item in items. Current row value will be equals to item at row index, and if current row value is equals to row value, then we will do matches plus equals 1, and let's define matches on line 37, and this looks great. So once we're done, we can return matches. So I will now delete all of this because that's pretty much actually the implementation. So at this point, let's try tracing this current algorithm we have to ensure that it's right. So let's try with the first item. So currently, let's say the row index is equals to, let's try row key equals to color, row value equals to silver. So row index in this case would be row key to index. You pass in row key, we pass in color into this dictionary, and we get back row index equals to 1. And matches in this case would be 0. And let's set the current item to the first item in items, and the current item is phone blue pixel. Okay, let's do this. And at this point of time, current row value will be equals to item at row index 1. So in this case, it will be blue. So current row value will be equals to blue. And we will check if current row value is equals to row value, which is silver. So in this case, this is false. So we will skip this and we will continue. So let's set item to the next row. So this is, yeah, let's move the comments a little closer so that it's more readable. So now current rule value is equals to silver at index 1. So in this case, this current rule value is indeed equals to rule value. So this will be true, and we will increment matches by 1, giving us 1. And we will continue to the final iteration of the for loop, giving us phone, gold, and iPhone. So in this case, the current rule value would be gold, and this will evaluate to false. So we do not increment anything for this. So yeah, that looks great. So yeah, this algorithm will work fine. Let's run this against some test cases. Looks great. Let's submit this. And there we go. Pretty decent. So items will range from 1 to 10 to the power of 4. So if we let n to be the size of items, and in this case, then the time complexity, because we do a linear scan across all items on line 27, the line 28 to line 30 are all O1. Item access by least access by index is O1. Comparison is O1. Increment is O1. So everything under the logic of each iteration is O1. So that's pretty simple. And because we do this for loop, in this case, this will be On in time complexity. And looks great. So in this case, the time complexity will be On. If n is the size of the items, this algorithm will scale linearly with the size of items. And for the space complexity in this case, we have a static size dictionary. So this doesn't change with respect to On. So space complexity for this is O1. And we only use integers to keep track of the number of matches and the rule index. And the rest of the logic over here doesn't use any additional memory that scales with respect to items. So this is great. So what this means is that the space complexity of this algorithm we are using is O1. So yeah, that's pretty much it for this algorithm. And that's it for this question. If you find this useful, please give us a like and subscribe, and we will see you in the next video.